My name is Mike Zimmerman. I'm a professor at Tufts, and I've been working in the field of material science for about 30 years. And the last 15 years, I've been working on state-of-the-art battery materials and technology. So the talk is going to be about some fundamental safety and materials issues, which are limiting advancement of both lithium ion and lithium metal batteries, basically. So the outline of the talk is I would like to speak about the energy industry, and batteries are part of that, and we're trying to solve a very important problem with batteries. I'd like to give a brief overview of the history of batteries and how we've arrived at the current lithium-ion technology. I'd like to talk about lithium-ion battery technology and its challenges. And I'm going to focus on the fundamental problems in these batteries, which are preventing them from being safe. And I'm going to be speaking about some new research that we're starting at Tufts, which is to be characterizing, understanding key issues relating to materials and battery safety. So batteries, again, it's solving an important problem. The overall energy industry is a very, very important industry, and it clearly needs an overhaul. Worldwide, there's 10 to the 17 watt hours used of energy per year. And right now, there's actually 91% of that comes from burning carbon-based fuels. A third is used for transportation, and about 2/3 is used for the grid. And as probably people realize, it leads to wars over resources, human rights abuses, pollution and climate change, and economic inequality. What's happening now is, and you've heard this in the news, but batteries, there's a push to enable oil-free transportation. There's an effort to go from internal combustion engines to battery-powered electric vehicles. We believe that EVs are much cleaner than natural gas. And essentially, one of the big issues now, though, is that in charging cars, the electricity still comes from non-green sources. So one of the big areas of effort right now in the battery industry is to develop batteries that can enable electric vehicles at a reasonable price. And one of the major issues that I'll talk about is the safety issues, which is basically one thing that's holding back the development of cost-effective batteries. Batteries can reduce the amount of coal burned by the grid. And right now, as I mentioned, we're still charging automobiles, electric vehicles, by using coal and other types of fossil fuels. And if we can develop low-cost, safe, and effective batteries, we can definitely reduce the amount of coal burned in the grid. The other challenge is batteries. We hear a lot these days about solar and wind, and we have to be able to store that energy. In order to make solar and wind cost-effective and to be a high-volume solution, we also have to solve the key technical challenges associated with batteries. So the history of batteries, it started out in 1799 with basically a copper and zinc electrode and a brine electrolyte. The first rechargeable battery that actually became commercial was a lead acid battery. And after that, from a rechargeable point of view, there was nickel cadmium battery. And that was a rechargeable battery right around 1900. And then in the 1950s, improvements in energy density came from things like nickel metal hydride batteries. And also in the 1950s, what was invented was the primary alkaline battery. In 1991, what the technology created there was by several people, and that was the advent of the lithium-ion battery. Actually, the original intention was to make a lithium metal battery, but there were problems with safety, and what was developed was a graphite anode. Recently, last year, there actually were three Nobel Prizes awarded to the inventors of the lithium-ion battery. So lithium-ion is the technology of choice for high-energy applications right now. The anode material is a graphite anode. The cathode material is essentially a 4.2 volt material. And what is the efforts right now are going to nickel, manganese, and cobalt for the cathode material. And the goal is to be able to push the voltage higher and higher, up to 5 volts. And a lot of the, over the last 10 years, a lot of the improvements have gone into the electrodes. And as I'll talk about later, the electrolyte is a liquid electrolyte, and some of the improvements going into that is to try to create a solid electrolyte to enable lithium metal and to hopefully improve some of the safety considerations. So the challenges, I'll just summarize them simply, is number one, safety, and that's what I'm going to talk about today. Cell chemistries basically cause safety issues, which can result in thermal runaway. And a lot of the battery packs have designs such that they put expensive components in weight and size to minimize the safety issues. Energy density, we want higher energy density batteries. We want to be able to have them smaller and lighter weight. And again, the energy density is being limited by the safety. And cost also is a major issue in lithium-ion batteries. We want to be able to make them cost-effective so that we're able to make things like electric vehicles for reasonable costs. So the major issue that people hear about in the news is the fact that the liquid electrolyte is volatile, and there's been many reports about airplanes, things going into thermal runaway, things like Teslas, where the battery goes into thermal runaway, and the problem is it's very difficult to put the fire out. There's been news about laptops, basically, where the batteries do explode, and it's being blamed on the liquid electrolyte, which is volatile. I'll talk a little bit more about that. One problem, this was a problem a couple of years ago in Santa Barbara. There was it was a boat where there was a bunch of scuba divers, and they were charging their lithium-ion batteries overnight, and they actually went into some sort of thermal runaway, and they killed 34 people. This particular event is kind of near and dear to me because I know the owner of the boat, and he was telling me about what happened, and there were 34 of his friends that were killed due to the thermal runaway problem with this with lithium-ion batteries. So it's this thermal runaway problem with batteries is a real problem. The cell chemistries have direct impact on this thermal runaway problem. Typically what happens is that you have some decomposition in things like something called a solid electrolyte interface layer. It generates heat, and then the electrolyte in the anode itself actually heat up, and it can run up to 100 degrees centigrade. The temperature goes higher, the separator starts to melt, and at about 200 degrees centigrade, you can have combustion, and the cathode drives further thermal runaway. On the right-hand side of this slide is basically one of the fuels for this fire, which is certain gases plus oxygen get emitted from the cathode material, and that results in being the fuel to cause a fire. And the chemistry and the actual chemical composition of the electrodes basically are what causes combustion and thermal runaway. One of the solutions for safety is basically, there's been a lot of work, particularly in the last 10 years, of replacing the liquid electrolyte with solid electrolytes. There's two main classes of solid. There's the ceramics, and then there's polymers. Both still have challenges, which is preventing them to be used in commercial batteries. And people have been working on these solid electrolytes. Michael Faraday actually invented and proposed the first solid electrolyte in 1839. But again, as I mentioned, there's two classes. There's inorganic ceramics, and that's dominated by two different classes within that. One is garnets, or LOZO, and the other is a sulfide glass electrolyte that's made, and actually Toyota is one of the major development companies that's working towards solid state batteries using sulfide glass. And the mechanisms of ionic transport are basically hopping due to defects in these materials. And until recently, these only worked at very high temperatures, but there's been some innovations recently which have allowed them to go to lower temperatures. But with the inorganics, there's still challenges. You have to make them stable against lithium metal, and there's been improvements in that. Some things like sulfide glass have difficulty in being stable against high voltage cathodes. Then people put coatings onto the cathodes to minimize that. Shorting is continuously a major issue, which is dendrites from going through the separator from lithium metal. And that's a major defect, which can lead to thermal runaway and other events. With the inorganics are more difficult from a manufacturing point of view, how to scale up large volume manufacturing, which results in higher costs. And as I mentioned, there's been progress. It used to be these would only work at high temperatures, but now they're actually working at lower temperatures. The other class has been polymer electrolytes. These were initially used in batteries. There's something called polyethylene oxide that was developed in the 1970s. In the 1980s, Michel Armand started working with those in batteries. Polyethylene oxide, the material itself is inherently ionically conductive, but essentially it only works above the glass transition temperature at high temperatures. So you have to heat the battery. And also, it does not work for the latest high voltage cathodes. But there's people continuing to work on this, and there's people continuing to work on other innovations in polymer electrolytes. The main issue with polymer electrolytes is basically having them have high conductivity at room temperature. So I'd like to now talk about safety with these different types of materials. The traditional battery has a flammable liquid electrolyte in it, and that has the conventional safety problems I've been discussing. There's also solid state batteries with a cathode and an anode in a solid state electrolyte. A lot of the ones that are being proposed for the market, because of the issues at interfaces and lower conductivity, people put a traditional carbonate type liquid electrolyte into it. So it's not completely solid. And there are all solid state batteries being developed. There's no liquid electrolyte in it, but there's still not proven that these are completely solve the safety issues by using solid electrolytes. There's been some work done. I'm quoting here a recent publication where someone analyzed what happens during different types of abuse testing. And one of the things that was determined was that with, for example, an all solid state battery, this one that was analyzed had LLZO, it was safer going to higher temperatures, but it was not safer when there was a dendrite breaking through the electrolyte, because the oxygen actually caused bad reactions with the lithium metal. So one of the points here is that it's been thought that by replacing liquid electrolytes with solids, it would completely solve the safety problem. But with my work in the industry and some recent reports, it's not clear whether that's really true. There's been methods used. So as I mentioned, one of the root causes of thermal runaway has to do with bringing fuel to the fire, things like oxygen release. And I believe that this oxygen release is a major root cause of thermal runaway. It's been somewhat studied. This is from a review paper I found. It's been somewhat studied by in situ calorimetry in the operando X-ray and thermal imaging, thermal analysis, time-resolved XRD, TEM, computational modeling. But there's things that have been lacking in this. And what I'm working at Tufts is basically working on a new effort to actually research new methods to measure the total amount of gas, both dissolved gas in the electrolyte and the evolved gas in the headspace, and to collect electrochemical data in lithium-ion batteries to better understand the root cause of cell safety and thermal runaway. So in essence, what my research group is trying to do is to actually study the actual root causes of fundamental safety in the current lithium-ion batteries with liquid electrolytes, and also with the newer solid-state ones. The kinetics of gas generation, we want to basically determine that and correlate it to data of heat generation and electrode surface changes. So this research, we think, will allow a deeper understanding into the fundamental issues that relate to self-safety and better define the cell safety problem in lithium-ion batteries and solid-state and all solid-state batteries. And if anyone is interested in collaboration, here is my email address.